Hi guys, I'm Frank. Today we are going to learn the detail about the signature and verify signature procedure of the ECDSA. And I have written a program with Golang to demonstrate the procedure. So at first, I define a variable private key with a hex string consisting of 64 characters. You can see this. This is the private key. The private key must consist of 256 bits, which is equivalent to 22 bytes or 64 characters of a hex string. This is the 64 characters hex string. And then I create a nonce manager instance, which is used to get the next nonce. Each train and account have an indefinite nonce and must be incrementally increased without gaps. And there is a respective value of nonce in the local client and blockchain. The nonce manager have to get the bigger of them as the current value. I last invoke the signature function. This function will sign the transaction message with the private key and verify the signature. And now let's look into the function. So in the signature function, at first the function define a variable to address, which is the address of our object account. Let a hex string consist 20 characters, which is gotten from public key of the object account. So, this is the to address variable and then validate the format and the length of the hex string of private key. Check if the hex string has exactly 64 characters, and check if the hex string contains only valid hex characters. Then the function invoke the function hex to ECDSA to character a private key instance. In this function, the hex string private key will be translated to a byte slice, which length is 32, and get the public key include x and y from the private key byte slice by the scalar multiply of the elliptic curve. This is the function. And then the function invoke the function public to address to get the address of the sender account. In this function, the byte slice of public key X append the byte slice of public key Y to 64 elements byte slice. Then the result byte slice is hashed by KECDSA K256 and then get the last 20 characters as the address of the sender account. This is the public to address function, and then we have and then we begin, and then the function began to construct a transaction instance. Set the chain ID to 1. It means this is a mainnet transaction, and use the and get the next nonce value by nonce manager, and then construct a transaction instance with the struct blob transaction, which is the newest transaction, and it has all feature of the Ethereum. I'll introduce the transactions detail in the other videos. Then the function create a signal instance by the new progress signal function. It's the newest signal which supports all EIPs. For example, EIP 7702, EIP 4844, EIP 1559, and EIP 2930, EIP 155. I'll introduce the EIP's detail in the other videos. Then the function invoke the function sign transaction, which will encode the transaction manager to the RLP code, and then hash the RLP code by the KECDSA K256. In the end, assign the hash string with SECP256K1. Put the signature result value VIS to transaction. This is the function of the function sign transaction. Then the function use the raw signature values function to get VIS value from the signed transaction and print them. There are some regulations. First, the R must be between 1 and or the N. Second, the S must be between 1 and a half of or the N. And now the V value is 0 or 1, not any more concern the train ID, because the train ID be consistent in the transaction messenger. So the V didn't need concern the train ID, and then the function validate R and S values against SECP 256K1 curve parameters. Check if R smaller than the order n, and check if S smaller than the half order n. And in the end, we invoke the function to verify the transaction. So in the verify signature, at first the function creates the same signal as the signature process. It is the project signal, and then hash the transaction manager with the signal. So we got the message hash, then get the RSV value, and construct the single bytes with them. The single bytes length must be 16.5, and then validate R and S value against SECP 256K1 curves parameters, and the function recover the public key from sign bytes and message hash, and so we got the public key. Then the function get the address from the public key. We at least invoke the verify signature function to verify the signature by the function verify signation. If the function return the true, it mean signature is the signature is right. And so this is the videos I made today. Thank you very much.